Thank you, Don. Okay, so I think that what Don was saying was the continuation of what I was saying here is our activity this week then is now we're going to jump into chapter 12. We'll finish up chapter 12. You have a test coming up on Monday. Don is doing the review for you on, and he put it here on the board. Must be Saturday, 1 o'clock in here. I'd encourage you to take advantage of that. Take advantage also of our Friday workshop with Don. So you've got today, you've got Don on Friday, you've got Don again on Saturday, and then you've got the test on Monday. And as you know, this has been the more advanced material that we have seen, and so hopefully it's beginning to sink in. The good news, both today and actually last time, is there's no new physics. That is, we're going to look at chapter 12, but you're going to see there's not any new material. It's a continuation of the same material. So that's good, because last Monday, 2 days ago, all I did was examples from chapter 11. So that means the last time you saw anything new was a week ago from today. All right, so that means almost 2 weeks, 22 days from last Wednesday till you take the test, there was nothing new. Now, that's not to say it's easy, but what it is to say is I think that's a fair amount of time to give you the last piece, conservation of angular momentum, and you to digest it. And I know you've been working on it, and I would assume you've come a long way, and I would also assume you've got a lot more to do to get ready for these. And as you guys saw me do the problems on Monday, those were really good problems. They were not softball problems. They were some good ones that really showed the meat of it. And most of you followed along. I suspect a number of you probably were still a little questionable in your own mind is, could you do that on your own initiative, which is what you need to do when it comes to the exam, but practice those. And so like Don had said, and when I walked in here, he was talking about, I guess, the review. I guess there's a, he's got the third review recorded on our YouTube channel here. But as you know, we've got the video camera in here, and on Monday, we recorded all of those. So I would encourage you to review those. Those were good problems. And so besides doing the homework, test yourself. You know, go back and review the videos, go back and review the examples done in the book and in your notes, but also test yourself. Just really go to chapter 11, open up the book, and just blindly pick at a problem and go, hey, number 44 looks interesting. I'll give that a shot and see if you can do it. Those are some of the best ways to practice. Just go, hey, I'm going to try number 44. Now, that wasn't easy, or maybe it was easy. I'll try this one. How about 63? Try that one and just pick them at random and give yourself, remembering that you've got, on average, 25 minutes per problem. The first problems will probably take a little bit less, and the last problem a little bit more than those 25 minutes. Now, that being said, also, let's look at the point distribution. Remember, we got the third test coming up, which is roughly 16 2/3% of your overall grade. Well, I guess that's not roughly. That is the percentage of test number 3. You got the final exam coming up in, was it 3 weeks, 4 weeks? Coming up quickly too. That's 25% of your grade. So what are we looking at? 25, 35, 30... I forgot what I said. Was it 16 2/3 and a half? So, I'm going to have to write it down. So, 25, and I'm just going to call it 17. There it is. So it's 42% of your grade is still out there in tests, right? We've got some homeworks and some labs to do still. What do we have? Like 3 more labs, which is about a percentage each. So there's 45%. Although you might already be factoring that in to your overall grade. Homeworks. Some of you have turned in some 9, 10, 11. Some of you are still needing to turn in, but 9, 10, 11, 12. We'll jump over to 13 and 14. There's almost half of the homework, not quite. I'll call that another 4%. Simply put, never forget this, half your grade's undecided. If you've been doing well, great, keep it up. If you haven't been doing so well, a lot of room for improvement here. And as you can see, the points are heavily distributed towards the end, as they should be. We've spent the whole semester learning the material, and now we've really got there, right? We've done our kinematics, we've done our Newton's laws of motion, we've done our 3 conservational principles, we've done objects now that have size, we've let our objects rotate, and we've got a lot of difficult questions now we can deal with. And when we read that question, we have to pause and say, okay, now how do I handle this problem and the good news is, you know, it'll be a mechanics problem. We won't be any optics or thermodynamics or any E&M. That's next semester, all right? But you got to ask, how do I do this problem? Do I use Newton's laws of motion, or do I use conservation of energy? Do I use those kinematic ones? Is it a rotational problem? Do I have to use the rotational principles? What do I have to use to solve this? And that's some of the hardest things that, of course, you gain by experience. And so let me take this then as an opportunity to say, okay, you know, these are the decisions that, well, I guess you've got to kind of figure out at the start of each question. Obviously, you know that this test coming up, there's going to be something covered in chapter 9, which 9 means we have things like center of mass and conservation of linear momentum. You know, or 10, which has to do with all those rotational kinematic stuff. Or chapter 11, which you know has to do with angular momentum. And back in 10, don't forget the torque, because what you'll see here in chapter 12 is chapter 12 will be more questions on torque and Newton's second law of motion, both translational motion and rotational motion. Well, I'll use this then as an opportunity to say, all right, what is going on here in chapter 12? And chapter 12 is static equilibrium. And as I said a few moments ago, you will see that there's not a new principle to discuss here. The same basic principles we've been doing that we finished up 7 days ago, we're going to keep talking about in this chapter and give you 5 more days to work on this. It's called static equilibrium because here's the idea. What if I had an object? Let's say the object looked like this, so some odd looking object, who cares exactly what it looks like? Oh, let's just say that odd looking object was able to pivot or rotate around that point. So for whatever reason, it can be, and I'll put an arrowhead, I go both directions here. Maybe there's a little nail put into the kind of the edge of it, and so I'm going to take that piece of wood and drive a nail through it. So now it could rotate. Of course, I could put the nail anywhere I want, right? So maybe I'll put a second point here, maybe here. Or maybe, just for illustration purposes, maybe there is no nail at all, and this object is sitting on maybe a frictionless table, or maybe even floating in outer space. So there's no particular axis of rotation. So it may have an axis of rotation, it may not, and that's what I'm trying to illustrate in that picture. But if this object then is, say, being pulled this way by who knows what force, maybe it's just as simple as a string tied to it and somebody's pulling on it. But maybe that's not the only thing pulling on it. Maybe there's another string over here, so maybe I should call this force 1 and this force 2. In fact, this could continue on. Maybe there is a third force. Maybe it's tied on down here. And of course, it could be a fourth or a fifth or a sixth. And let's not forget that there's probably a gravitational force. If it was flat on the table, like I was saying, then I could kind of ignore the gravitational force. If it was, though, actually in a vertical plane this way, and there was a nail driven here, there might be a center of mass right there. And so there would be the force of gravity. So that would be another force that's not necessarily coming from these strings that are tied to it. But here's my point, and this is the point of the whole chapter. If this is going to be in static equilibrium and stay there, so maybe we should pause. What do we mean by that phrase, static equilibrium? Yeah, not moving, right? It's stationary there. So what would you say then about the acceleration of that object? 0, right. But here's why it follows the last chapter. What would you say about the angular acceleration? Also 0. And so that phrase, static equilibrium, like a building, what we mean is we want that building to be stationary. And stationary means both stationary in translation and stationary in rotation. So if the building moves left or right or up or down, forward or back, that's not a good thing. But just as bad is if the center of mass stays where it is and the building spins. Okay? Well, if we want static equilibrium, we want both translational and rotational accelerations to be 0. And so what that would mean in terms of translational motion is the sum of all the forces would have to be 0, right? Because if they're not 0, then we get an acceleration. We get an acceleration in the direction of those forces. That is Newton's second law, and I'll say of translational motion. But there's also the torques. And what would you have to say about the sum of all the torques? Yes, they've got to come out to be 0 also. And so you can see why this chapter is kind of, following the chapters we just did. The first time we did a set of chapters that can allow things to rotate. And so now we are getting into scenarios, or are going to have a whole chapter here. It's not a long chapter. And like I said, it's not any new material. It's a whole chapter on saying there are many times what we want is static equilibrium. We want our object to be stationary. And that means not only stationary in terms of translational motion, but also stationary in terms of rotational motion. Both of those conditions have to be met. And so if you've had a chance, or when you get a chance to look through chapter 12, you will see that your author, this is the first section, your author says, what do we mean by static equilibrium? This is it. This is the whole lecture on chapter 12. There's really not much to lecture on because there's not any new material. It is taking what we've learned and putting the concept here and saying there are times where we would want the ropes over here to have enough strength so that the object doesn't rotate. So the question is, how strong does the rope have to be? Questions like how much tension needs to be in that rope in order to get our static equilibrium. So what I want to do for you today is jump right to the examples then. Let's just go to the end of the book. Let's just set it up and start doing some examples and start calculating and showing you that the best thing I can do here is just some direct calculations, because as I said, there is no real new piece of physics, no new principle like Newton's fourth law of motion or anything that needs to be discussed. It is just apply what we've been using. And I think I have 37 written down in my notes for this first one. I call this the bear trap problem. Yeah, it's a good one to lay out exactly what we've been saying. So let's run through it. Let's see what we mean by static equilibrium here. And so it says here in 37 that a hungry bear weighing 700 newtons walks out on a beam in attempt to retrieve a basket of food that is hanging at the end of the beam. So it's Yogi, right? So here comes Yogi walking out at the end. And it's a bear trap. You can see the bait at the end. So there's the basket of food out at the end of it. The basket weighs 80 newtons. A says, go ahead and draw the free body diagram. B, when the bear is 1 meter out, find the tension in the wire and the components of the force exerted by the wall on the left end of the beam. And then C, what if the wire can withstand a maximum tension of 900 newtons? What is the maximum distance that the bear can walk out? And so there's a lot to be said about C, but I think we need to kind of understand the problem before we get there and do A and B here. So I will try A first and encourage you to do the same. It's no different than we've been talking about ever since chapter 5. Chapter 5, I said, number 1, get a good physical picture of what's going on, and then number 2, draw the free body diagram. And so even when we got into our rotational motions in this last unit we've been doing, it's the same idea. Draw the free body diagram. Of course, now we have to think about things rotating, not just translating. And this problem, we want to think about both of those, because this beam, if I were to draw it, would look something like this. And a free body diagram is to draw just the beam. So I'm not going to draw the bear. I'm not going to draw that wire that is connected to it, the goodies or the wall there. But as I go to write out the forces, what forces are on this beam? Well, I suppose one of the easiest one is the fact that the basket is hanging at the end of the beam and pulling it down. They said it was 80 newtons. All right, there's a simple one. But you guys help me out with the rest. What other forces are here? Okay, the fact that the beam has a gravitational force. Where do I draw that in my free body diagram? Right, that's why we did chapter 9. And when you get a chance to look at your chapter, that's actually section 2 of the chapter. The author says, don't forget about center of mass. So he repeats everything he said in chapter 9 about center of mass, and he repeats it again here in chapter 12, noting that what we learned in the past about torque was a force and the distance associated with that force. So we need to know where the force is acting, and that's why the center of mass comes back up to our discussions here. And so this beam has a center of mass in its center spot if it is a nice uniform beam. And I think they say that, don't they? Walks out on a beam. Well, they probably should have said a uniform beam, but I think the picture shows. Oh, good. Oh yeah, later on there, the beam is uniform. Good. So the beam is uniform and it weighs 200 newtons. And so the whole idea of uniform is to get you to realize where the center of mass is. Making it simple in terms of where the placement of the center of mass is. Not to say the problem is simple, but they made it a lot easier on us by telling us the beam was uniform. We know where the center of mass is. All right, so there is 2 of many forces. What other forces are here?
Tension.
Tension from? Okay, the one on top, not the goodie bag, right? Okay, so you're saying that there is a force here. What direction is it?
Top left by 60 degrees from the horizontal.
You see, here's where I want to have a quick discussion here. They show the direction of the rope, the cable. Is that the same direction as the force? So I'm sure not a surprise that I just happen to have a rope right here. But if I were to come over here and take this rope and tie it onto something, say here, I'm sure it doesn't surprise you that what I could do with this rope is actually kind of limited in the sense that, could I pull on this? Yeah, I could pull. Could I push? So right away, you see that things that are flexible, ropes, string, cables, chains, you can't push with them, right? So we call this tension. We call this compression. So we say ropes and strings and cables and chains, they can all have a tension but not a compression. So that tells me a little bit more that the force has got to be that way, right? It can't be in the direction of the rope. In fact, another neat thing about ropes or anything that is flexible is, what if I try to make a force on here that is slightly different than the direction of the rope? In other words, I can pull the direction of the rope, but what if I kind of twist the rope? Could I push this down by twisting on the rope? No. Now, the reason I bring that up is, what if it wasn't something flexible? What if it was something that was more rigid? Let's say it was mounted on there. Could I push? Could I twist? Yeah, and I would say if I'm holding this here, the force on this object is kind of down at an angle. Notice it's not the same direction as the beam. So notice that things that are stiff, you can actually push in such a way that the force on this object is not the same direction as the beam itself. We call this sideways a shear. So what's nice about things that are flexible is they only have tension. You can't make them shear, and you can't make them compress. And I brought this up because when you look at the direction of this rope or cable, whatever this is, you know it's flexible. So do you know the direction of that force? Yes. It's the same direction as the cable itself. So I can argue that they have shown, the angle, 60 degrees, of the rope, and I know that is also the direction of the force. And I know it is a pull away. Now I brought all that up because there is also a force, this wall, on the beam itself. It would be acting on this end of the beam. What direction is it? So here's the beam. This is then mounted here. Does the force from this wall have to be in the direction of the beam? Couldn't this, I'll use my hand, be pushing it that way? Couldn't this be pulling it that way? Couldn't this also be pulling it and twisting it? So if I were to let go with this hand, it would go like that. Right? So there's a lot of things and a lot of directions this can be pulling. And that's going to make our problems a little bit harder. And that's what I wanted to point out right away in this first problem. Look for things that are flexible because they are the easy ones. You know their direction. But remember also that when you have rigid objects, the direction of the force from them is not necessarily the same direction as that beam. So when I come over to here, how do I draw the force from this one?
Well, it's going to have to go to the right somewhat because there's another force on the right going.
Exactly. I know, and this is what I'm trying to point out, that unlike this rope, I would not draw the force that way. It could be that way. It could be up. It could be down. It could be both of those at the same time because it could be off at an angle, right? So let's do this. let's just say it has an X component and it has a Y component. And we have no clue how big those are because they are being applied on a rigid object. And that's what I wanted to make sure you saw here. And as you're pointing out, they would have to have both. If you just come and look at the static equilibrium of this, you begin to see that without a force going in this direction, you would never get it balanced left and right because the tension from here does have a component to the left, hence I must need a component to the right. Fair enough? So I know this definitely has a component to the right. Likewise, I know it has to have an up component. You can see that I've got stuff pulling down, which of course means I must have just as much pushing up. That by itself doesn't say I have to have an up, because the up component of this could be enough to balance the downward. But when I look at the rotation, and that's the stuff that's new to you, imagine this. Think about it trying to rotate around this point. These guys do not make it rotate, but this does. Hence, I have to have an upward force here to balance the rotation. And maybe I should use this as another opportunity. Notice I analyzed it in terms of rotating around this point. Although when I think about this problem, I think the most likely thing to happen is that this cable is going to break, and then what's going to happen? It's going to rotate around that point. And what I was setting up was, in this problem right here, if you want the acceleration to be 0, don't you want the acceleration to be 0 around any point? And so remember this, you can calculate the torque as measured by any point, and it should come out to be 0. Because what if it was not 0 around some point? What would happen? Then it would rotate around that point. The whole idea of static equilibrium is it is not going to rotate around that point or any point. So if we look at it as a rotation around this point, we can see that these two are making it rotate in a clockwise and this one in a counterclockwise. Sure. And those have to be balanced just right. If I think about it as rotating around its center, this one makes it go clockwise, this one makes it go counterclockwise. This horizontal piece doesn't do any rotation, but this one does a clockwise. And so these two together are making it rotate clockwise. It needs to be balanced by that one, which is counterclockwise. Or analyzing it from this end point tells me that this one is going to make it go counterclockwise, which is why this one needs to be here to go clockwise. And that's what I used as my explanation to make an argument then that this force on the beam from the wall would have to be made out of horizontal pieces as well as vertical pieces. Fair enough? When we don't know how big they are, we just know they have to have both. And so the summation of these two means that the direction of the force is really like that. And so even though I've drawn it to look like there are two forces on it, there's really just one, right? There's one force at an angle, and these are the components. But since we're going to break everything into components, it's probably better just to leave them as components. So that's why I put that in a different color with a dotted line. That truly is the force, but I'm not even going to look at it. I'm going to just say these are the components. And unless they ask for the overall force and direction, I will probably leave it in components. But I noticed that as they went on here, it actually said, find the tension in the wire and the component of the force exerted by the wall. So they're even asking me for the components. So I'm not even going to put them together. So they are looking for how much is horizontal and how much is vertical. And so that's what I will do here. But I guess I've kind of worked my way into part B, but let me see. Did I finish A? Did I get the free body diagram? Oh, no, I'm not done. There's one more force. What else is I'm missing here?
Bear.
Yeah, the weight of the bear. And so the bear is pushing down at 700 newtons. And of course, the bear in that diagram is labeled at some distance x from the wall. And I think they gave the length of the beam, didn't they? Let's see, hungry bear, 700 noon, walks out to retrieve. That's 6 meters, okay? And so the whole length of this is 6 meters, which is a nice way of saying then also that the center of mass is at 3 meters from the wall. Okay? And so there's going to be step 2 to any problem. Whether they say, draw the free body diagram or not, let me say the same thing I've been saying. That's step 2. Don't skip it. Very powerful step. It will help clarify your thoughts as you move forward. So step 1, good physical picture of what's going on. Yeah, I got that. They gave me a diagram, so that one wasn't real hard. 2, the forces. And the forces are everything touching it plus gravity. So the basket is touching it. The bear is touching it. The wall is touching it. The top cable or supporting cable is touching it. And then gravity. 5. 1, 2, 3, 4, 5. Yep, got them all. Everything touching it plus gravity. Okay? And now, step 3, write out the equations. So I know that all of the forces have to add up to 0. That is really a 2-part statement. The x's have to add up to be 0. And the y's have to add up to be 0. And then, of course, the other is that the sum of the torques have to add up to be 0. And since all of our forces are in the xy plane, each of those forces are going to make a rotation or try to make a rotation. Individually, they would make a rotation, but collectively, hopefully they make no rotation. But we would get a rotation around the z-axis. And so these are my 3 equations. 1, 2, 3. Which will allow me to solve for 3 unknowns, which is great, because those are the 3 they asked for. What is the tension in the wire, and what are the components from the wall? So 3 equations, 3 unknowns. Oh, by the way, I could even write out multiple more than 3 equations. They wouldn't be independent equations, so I don't know if they would do me any good. But remember, the torque has to add up to be 0 around what axis? Any and every axis. So couldn't I get almost an infinite number of equations out of this, because I could just pick another axis and say, okay, I'm going to calculate the torque here. I'm going to calculate the torque from here. I'm going to calculate the torque from here. I'm going to calculate the torque from there. And so sometimes that makes a real advantage. But I think for this first problem doing examples, let me just write it the way it is. Let's write out the forces in the x direction. So writing out the forces in the x direction, setting that equal to 0, I would look at this free body diagram, and obviously from the wall itself, I have F sub x from that one. The y component is vertical, the weight of the bear is vertical, the weight of the beam is vertical, the basket of goodies are vertical. However, the tension that is in that supporting cable is at an angle. And so if I take the magnitude and look at the adjacent of the 60 degrees, that would get me the x component. And noting that that x component would be in the negative direction, there would be my first equation. The sum of all the forces in the x direction is 0. And of course it has 2 unknowns in it, so by itself I can't solve it. But hopefully my system of equations is solvable because, as I said, I have 3 equations. And there are 3 unknowns. So I'm going to have 3 equations, 3 unknowns. And as maybe not obvious to you yet, but this won't be a hard system of equations. It's going to, you'll see that in just a second here. Sum of the forces in the y direction. Again, that has to add up to be 0. And so if I add these up, I get forces going up. There's the y direction. And that's from the wall. The bear is down, the weight of the bear, and the weight of the beam is down. So I'll go minus 700 newtons for the weight of the beam, minus 200, the bear, and the minus 200 for the weight of the beam. The minus the 80, that's the weight of the basket of goodies that are there. And then I get to that supporting cable again, which again, it has a component. So it would be the part that is opposite of the 60 degrees. So I will take the tension and multiply by sine of 60. And it's an upward force. And of course I can simplify this a little bit. This comes to be 980 newtons there. But again, you can see the system of equation. It has two unknowns in it. And when combined with this one, these are different, so that's three unknowns. So what I have so far are two equations with three unknowns. So again, I don't have enough equations to solve it yet. And then finally, the last one, which probably is going to be the hardest one for you since this is the newest material. But we learned about torques in chapter 10, that continued into chapter 11, and now continues into chapter 12. And I think I mentioned that when we were in chapter 10, that this is designed to introduce you to torque and just keep building on it and give you 3 chapters to digest it, and hopefully, and by then you'll be ready for the test. So after about 3 weeks of working with torque, you're probably getting much more proficient at it. Maybe still got a ways to go, and then we got 5 days before we get to the test, but it's getting close here. And so let's look at the torques. And like I said earlier, this could be the torque around any axis. So why don't we pick the one that is going to be the most useful to us? And I would say the one that is the most useful, it would be the one that was going to make these equations the easiest. And I'm thinking, let's calculate the torque around the left end of the beam. What did we see in these last chapters about the torque? About how much torque would I get from these two component of the forces here? 0, right? Even though we don't know what the individual forces are, we know that their distance from that point is 0. And since torque, and maybe I should put it here again, is the distance times the force times the sine of the angle between R and F, then this, if it's 0 for those two, then you're not going to get a torque. That means those unknowns are not going to show up in your equation. The only thing that will show up in your equation for torques are the ones that are not at your axis. This one will show up, but I know its value and its distance. Perfect. This one, I know its value and its distance. This one, I know its value and its distance. This one, I know its distance, but not its value, and I know its angle. Perfect. The only thing that's going to show up in that equation is one unknown. And that makes the math easy when you have one equation and one unknown. So that's why I'm going to pick that as my rotating point and say, all right, let's add up all the torques. And maybe for completeness, I will put 0 plus 0, saying I get 0 torque from this vertical component. I get 0 torque from that x component. How much torque do I get from the bear? And maybe I should emphasize, they do say in part B, when the bear is 1 meter away. So they're talking about at the moment when x equals 1 meter. That will change in part C, but at the moment the bear is 1 meter away, how much torque do you get from the weight of the bear? Well, looking at this, wouldn't the distance be 1 meter? The force would be 700 newtons. What's the angle? And remember, this is the angle between these two. So, isn't that 90 degrees right there? So the torque would be a distance of 1 meter times a force of 700 newtons times a sine of 90 degrees. And would this be a positive or a negative torque? Is it making it rotate clockwise or counterclockwise? Clockwise, which we traditionally have labeled as negative. So why don't I put the negative in there? Or, as we learned in chapter 11, you can use this great right-hand rule, which says, take your fingers and put them in the direction of the first vector r, and adjust your palm, in this case like this, so you can close it towards the force, which is down, and look at what direction your thumb is pointing. So my thumb is pointing in the negative direction. So, yes, the torque from the bear is a negative number. Distance, force, angle. Negative. How about the weight of the beam? How do I get the torque from the weight of the beam? Yeah, it's a distance of 3 meters. It is a force of 200 newtons. It is at an angle of 90 degrees, right? And is it a positive or a negative torque? Right. Negative. It's in a clockwise direction. I'll keep going. What about the basket of goodies? Yeah, it's 6 meters out, so there's the R. Has a value of 80 newtons. Has an angle of 90 degrees between R and F. And again, is it a positive or a negative torque? Negative, right? And so all 3 of these are rotating the beam in a clockwise direction. But let's go to the last one. The last one is the torque from this support cable. I'll start with, how far out is it? 6 meters. How much force do you get? Well, that's what we don't know and would love to solve for. That's T. What angle is it? Yeah, there's an angle of 60 degrees or 120, but the sign of the supplement are the same thing. So put a sign of 120 or put a sign of 60. And is it a positive or a negative torque? Positive. Why? Okay. Okay, if you look at this, imagine putting your finger here to hold it into place and pulling on it. If you were to pull on it, wouldn't that make it rotate in a counterclockwise direction? Okay. And so that is why I'd call it a positive. It's making it rotate counterclockwise. Not so much that it's up, but that it is in a counterclockwise direction. And if I use the right-hand rule even, I would put my fingers in the direction of R and adjust my palm so I can close it towards T, and then my thumb is pointing out the positive direction. So this is the positive torque. And that makes sense because I guess I didn't give myself room here. All that is supposed to add to 0. That was the condition of static equilibrium. That not only do the forces add to 0, but the torques add to 0. And so this is the one that I was saying is the one that is going to be the best one to really have done first. Because as you scan through here, there's only one unknown. And you can solve this then for tension right away. And so this would be, well, I'll put a negative 700 Newton meters from the torque there. This would be 600 Newton meters from the torque from the weight of the beam, the 3 times the 2. This is 480 Newton meters from the torque there. And so those are my 3 torques. And of course this one is a plus, and then we have that 6 times the sine of 60 degrees. Comes out to be about a 5.20 times T. And so now, after a little bit of arithmetic here, 700 combined with 600 combined with 480 divided by 5.2 gives me a torque of 342 newtons And I probably should have left my unit of meter in here, so that when I have my torques in Newton meters and divide by a meter, I get a force in newtons. And so there's the answer to B. What is the amount of tension in that cable? And of course, assuming that cable can handle it, then the bear's fine 1 meter out. In fact, they go on into C and says, well, what if the wire can withstand a maximum tension of 900? And so maybe you can begin to see what would happen as the bear moves further out. Well, as the bear moves further out, this number here is getting bigger, right? That means the negative torque created from the bear is getting bigger and bigger and bigger. So to keep the beam from falling, what has to happen here? More and more tension here, right? And so as the bear is going out, the tension is getting greater and greater and greater and greater. So right now, we're only at 342, but it can get greater and greater. And of course, if the rope or cable, whatever this is, goes to 900 and then it breaks, then it will fall. And so if there's a little net right under there, that's what's going to happen. It's going to break, going to go down, bear is going to get caught in the net. So that's why I was saying it's a little bear trap here. Then you can put on a new rope and let the next bear come along here. And you even use the same bait. All right, so there's this idea. Now to answer C then, let's do this. Let's change this last equation, and instead of putting 1 meter, let's put that as the unknown x into the equation. Go ahead and erase my free body diagram if that's okay. And say, all right, rewriting this then, 0 equals negative x. So there's that first one right there. Negative x. Where is the bear? The bear, 700 for the torque. Now, the torque from the beam is still going to be the same, so I'm going to go ahead and just write that as a negative 600 Newton meters, as we saw before. And the basket of goodies is still going to be the same, 480 Newton meters there. And then, of course, this is going to be 6 times the... And let me go ahead and put 900 in here. And basically what I guess I'm really saying by putting 900 here is, what is the value of x such that the tension has gone up higher and higher and higher until the tension is now at 900? So where is the bear? And so solving this for, well, I'll just do negative x times 700 and put all these together. So this one here is 6 times 900 times the sine of 60. That's 4,677. I'll subtract the 480 and subtract the 600. And so all of this together is 3,597 Newton meters. So now I can solve for x. I can move this over to here and then divide by the 700, coming out to be 5.14 meters. So bear almost gets there, so just beyond 5 meters is when the rope breaks and it swings down. Sounds like a good bear trap to me. The bear is significantly out there. It'll fall in the net, not quite close enough to reach the food. So gets there, rope breaks, falls down. Got the bear. Okay? And like I said, I thought would make a good first problem. Maybe not a very realistic type of problem. There's much easier ways to make bear traps than having them climb up there. Although for you backpackers, you know that this is a common procedure in terms of keeping your food safe by simply, when you go hiking and you get to camp, tie that food up in the tree, off on a branch, way out at the end, because any hungry bear, first of all, will go towards the food, not towards you, so you put it far away from you. That's a good option. Option two is the bear can't really get to it. The bear knows that if it goes that far out on the branch is going to break. And so they say, well, I can't get there. And they just can't get it. It's the same thing that the mother bear does for the little cubs. When big angry male bear comes around to kill little baby cubs, mama bear says, go up the tree, go up a branch, go out to the end, and that big 1,000-pound bear can't get you because that branch will not hold 1,000 pounds. That's a good safe place for little guys. Same idea for polar bears, but they don't have trees. They go up the steep mountain. And so you build a little snow cave up on a steep mountain, and no 2,000-pound polar bear can support itself on that steep one. It just hits the snow and comes tumbling down here. So good safe place for smaller objects, right? Anyways, this one though is more of a realistic one. This is what some of you will go into civil and mechanical engineering, and you'll be asked to calculate different numbers of structural strength of I-beams and how big or small do we have to make the beam, at what distance do we have to tie everything. And in this case, this sounds like during the construction of a skyscraper, we want to then get our materials up. And of course, we don't really have skyscrapers in the city we live in here, but major cities do. And it's very common then is you build the first couple of floors of the building, and then you build a crane on that top floor, and that crane is there so as the trucks drive on the street below, the crane can go down, pick up the gear, bring it to the top floor, and now you can build, say, a couple more stories, and then remount the crane and build a couple more stories and remount the crane and build a couple more stories and remount the crane. And so mounting the crane on the side is an important procedure, and of course you want it to stay there. You don't want this big old truck to pull up here, and here is this load of I-beams that we're going to put up on the top floor, and the crane goes down and grabs them and gets about halfway up, and the crane breaks and falls on the cars and the street and the people down below. So how strong does it have to be? And this is a good one that illustrates this. So let's read this together here. It says a crane of mass 3,000 kilograms is designed to support a load of 10,000 kilograms. So we're going to design it so that we can lift up to 10,000 kilograms, as shown in the figure. Now the crane can pivot with a frictionless pin at A, and it rests against a smooth support B. Find the reactionary forces at A and B. Now, like any problem, step one, let's get a good physical picture of what's going on here. So you got the diagram here, okay? And they give the crane, but here's the side of the building. And what we're going to do is we're going to mount it. And we got to make sure we make this support strong enough to hold this crane. And I should say, not just the crane, but while the crane is lifting up 10,000 kilograms. How strong does this little pivot? Now notice they say it's a pivot, because again, we would like this crane, when it's not in use, to be resting up here. And then swing down when the trucks come by underneath, and so it's just going to kind of touch at this point here, B. It's going to pivot around A, and so you can see what's really holding it up is A, but B is needed to keep it from rotating. You can imagine then that if you have something very, very heavy out here, imagine pulling on this, that would make it rotate here, right? So we need B to be made out of something very strong that it can push back in this direction so that it doesn't rotate on us. Fair enough? But at the same time, B is not really lifting the crane up or down. And so if I come over here and I say, well, let's draw my free body diagram. And let me emphasize that, again, step 2, make sure you always draw that free body diagram. So 41 is saying, all right, here's this crane. I'll just kind of do an outline of its superstructure here. But that point right there is probably a very, very large horizontal force, but no vertical force. So let me call this the force at B. And so there's kind of the first force in my free body diagram. All right, well, you guys help me out. What other forces are here? Yeah, everything touching it plus gravity. So let's go with the plus gravity. The weight of the crane. And so somewhere in this superstructure is its center of mass. And well, they've got it maybe angled a little different. Maybe more like that. Yeah. No, but they put the center of mass maybe, where the heck do they put the center of mass? Is it above point A? Yeah, it kind of is, huh? All right, so here's point A. We'll talk about that in a second. But the center of mass, they're putting maybe right about there. So there's the mg. And they even give a little dimension here that this is 2 meters. Not to be confused with the whole distance that it reaches out, which is 6 meters. So the crane's a little bit longer than 6 meters. I think they're saying here this is the horizontal direction that it is out. So again, notice that the center of mass of the crane is not the center of the object. This is not a uniform object. So they have put the center of mass there and kind of labeled it. They don't really tell me how high or what angle above A is, but they do tell me its horizontal distance. Now, the other force, as I heard somebody else saying, is not just the force of gravity, but the other things touching it, including this heavy load, and B and A. So the heavy load is pulling down with a force of 10,000 kilograms times 9.8. There's the mg. So there's the force pulling on the crane from the load it is lifting. So we got the weight of the crane, which maybe I'll put those numbers in the little diagram too, since I put the 10,000. They said the crane was 3,000. Okay. So got 3,000 from the crane, 10,000 from the load. And I heard somebody say the only thing I'm missing here is A. And of course A is probably this very large bolt, metal cylinder of some kind, something that's got to hold a lot of weight. It probably then is a rigid object. And so, as we were saying in the last problem, this force at A being a rigid object, I don't really know what direction it is. But what I do know then is whatever direction it is, I can label that in terms of its components. In fact, I would expect it to have components. I mean, let's just talk about the vertical first. I think that's the easiest one. I mean, for this crane to remain at rest here, clearly these two are pulling it down. So something has to be pulling it up. Yep, and that's exactly what that big old bolt is for. If we didn't have that, the whole thing would fall. I hope that's pretty obvious. But hopefully what's also obvious is there also needs to be a horizontal force. Now, probably not in the direction I indicated. It's probably opposite in the direction I indicated. And I think you can see that best. And again, remember this little trick. The sum of the torques has to equal 0 around what axis? Any and every axis. So imagine point B for a second. You could even imagine it was bolted at point B and the bolt at A was taken out. Wouldn't these forces make it tend to rotate around this point B? So what has to happen here at point A so that it doesn't rotate? Doesn't there have to be a horizontal force this way? And so point A does have a horizontal force. And I claim it will be in the negative direction. But I'm just going to put it up there and say, let's do the math. Let's see if it comes out to be a negative number. That's kind of what I expect. I expect there to be a very large horizontal force in the negative direction. And of course, we as the engineer would want to know how much that force is, because we're the ones who are going to have to put a bolt there. And that bolt is going to have to be big enough and strong enough to hold all the conditions that we're talking about here. And as you'll see, it is far larger than just the 10,000 kilograms that are needed to, that it is designed to lift up. This bolt's going to be many times greater than that. In fact, you're going to see the cause of that is really because of the torque, because of the long distance of 6, and the torque because of the short distance of 1 meter. Because we've got to balance the torques. We don't need to balance the forces. Well, we do need to balance those too. But the forces have to be balanced as well as the torques being balanced. And that's the conceptual picture in there. So that's why they gave us that distance between A and B as 1 meter. Well, with that being said, let's do the same type of logic. Let's add up all the forces in the x direction. We know all the forces in the x direction have to add up to be 0. So let's give it a try. In our case, we have the force at B and the force at A in the x direction. That has to add up to be 0. That equation mathematically by itself makes it very clear one has to be positive and one has to be negative, right? The only way they're going to come out to be 0 is one is positive and one is negative. And we already argued then that B would need to be in this direction, the positive, and A needs to be in the other direction, has to be the negative. So that doesn't surprise me that one's got to be positive and one's got to be negative. Let's do the force in the y direction. The force in the y direction, same idea here. What I have are these two pushing down, and so I have the 3,000 times 9.8 going in the negative direction. I've got the 10,000 times 9.8 also in the negative direction. And the only thing I have in the y direction is the force from that pivot up there, that big bolt. And that has to equal 0. In fact, right there, I'm tempted to go to step 4 and solve the equation. But just to stick to our game plan, let me not, but because I can see I have one equation and only one unknown there. Okay? But my step 3 has always been just write out all the equations. All right, so I'll keep going here and write out the last equation, torque. And I'm going to ask it again, torque around what axis? Any axis. So let's pick one that's going to make our life the easiest. What would make our life easy? Well, remember, if there's any force at that axis, it doesn't show up in the torque equation. So I'm thinking A is a good place to pick because of that, right? Because these two unknowns are not going to show up in that equation. And only this one will show up. Perfect. And so let's pick the torque around point A. B wouldn't be bad either. Yeah, so let me do A anyways, nonetheless here. So as I look at the torque, why don't I start with the gravitational force? I guess that would be an R, an F, and a sine of the angle. And I guess it would be a negative torque. This force, of course, would be the 3,000 times 9.8. But it's the R and the theta that I might have a little troubles, unless you see the geometry here. Do you know what the value of R is? Well, isn't the R the distance to the center of mass? And we don't know that. And isn't this the angle between them? Which we don't know that. Looks like it's a little more than 90. However, if you make a triangle here, if this is R and this is theta, what is R times the sine of theta? Isn't that R sine theta? Isn't that what they labeled as 2 meters? So we don't know the individual R and we don't know the individual theta. We know the result of the two together. What's referred to as the perpendicular distance. And so that's what they gave us for this problem, the perpendicular distance. And that's a big reason I picked this problem. It kind of illustrates that whole scenario. So this is saying that the torque would be in the negative direction. It would be 2 meters when you take the R and the sine theta together and call that then the perpendicular distance. That's where the 2 meters came in. Again, don't know the R or the angle individually, but collectively, I know the perpendicular distance. And then, of course, the force is the 3,000 kilograms times the 9.8. So there's the torque I get from the weight of the crane itself. How much torque do I get from the load that it is hauling? And again, hopefully you see the same idea here. I'll draw it in blue. But when you go to calculate the torque, you might think you need the R. You might also think you need the angle. But you don't. You need the two together. And so making a blue triangle here, R times sine theta is this distance. That is the 6 meters that they've listed. So they've given me collectively the perpendicular distance, the lever arm. And so this is the 6 meters, and this is the 10,000 kilograms times 9.8. Okay. And so there's my torque from the load the crane is lifting up. Not done, because then this force here, B, is that distance away, right? And so its value of R is 1 meter. Its force FB is unknown. That's what I would love to solve for. I think they want us to point out that that's 90 degrees. Do they make that clear? They kind of show it in the picture that they're right on top of each other. So if you were to draw a line straight down, they would be, you know, A and B would be right on top of each other. So we would be at 90 degrees. And of course, this would be pushing it in a counterclockwise direction. And so again, you can imagine kind of holding it here with your finger and pushing this way. That would make it rotate in a counterclockwise direction. So that one is a positive torque, which of course is what we need to balance these two negative torques, and that has to come out to be 0. Okay. And so, again, I like this equation because it has only one unknown in it. So it looks like this equation and this equation are going to be pretty easy to do. They give me two of my answers right away. And of course, once I know f of b, I can get that one. So I don't know which order you want to do it in first. Maybe I'll do this one first, but this tells me the amount of force that is going to be on that wall. And of course, we better make sure we build it strong enough. Otherwise, this heavy load is going to push in and crush the wall that we just built. Right? And so we want to know how much force that is, so we build it strong enough. So taking these numbers, let's see, that's a 2 times a 3,000 times a 9.8 there. And it's a negative. Let me subtract then the 6 times the 10, 1,000 times the 9.8 there. Combine those two. Move them to the other side of the equation. Now they become positive. Divide by 1, divide by 1. And so I get a force of 646,800 newtons. Huge force, right? Far greater than the amount of weight we are lifting up. So again, we're going to have to build this wall very, very strong in order for this to work. And again, not a surprise, because these two are pulling it, so there's two of them compared to that one, and their distance out is much greater than this distance. So this force here has got to be just a really large force in order to get the same torque at that short distance of only 1 meter. And so that's why it comes out to be a huge force. And we're going to have to, like I said, make a very, very beefy wall here. If we don't, this isn't done right, this whole thing's coming down. Won't take too much to knock it down. Now, force in the y direction is just, of course, these two downward ones, the 13,000 kilograms going down. So 13,123 times the 9.8 says that the upward force here has to be 127,400 newtons. And then this one here says that the force at A in the x direction is the negative of the force at B. And B was this very large force, 646,800 newtons. So it would be the negative direction. And so again, whatever this is made out of, it's got to have a very large force. It has to have this much in horizontal and then this much in the vertical. And of course, if we add those two together in the right angle, so we would have to add them in quadrature. But if we do Pythagorean's theorem on it, we will see how much force that is. And so that's a pretty big force. So we better make sure we make it out of a pretty good bolt. You're not going to make this out of a piece of wood, you know, like a dowel piece of wood, like you might make a closet out of. It's just not going to hold that much, right? It's got to be probably metal. It's got to be very thick and very strong. Well, I think you're beginning to see the idea, and I hope so, because the only thing I want to do here for today is, again, more examples. So just like Monday, just want to do a bunch of examples for you, and just like today, I just want to do a bunch of examples for you. Workshop, and you do the homework, a bunch of examples. Come Saturday for a review, a bunch of examples. And so I think you'll have more than plenty of examples to see. Your big issue is to make sure you do the work too. Make sure you can do all these on your own here. All right, let's look at 43. 43 is the same idea, that we have this object. If you're on a fishing pier, not kind of our recreational pier here, but these fishing piers, there'll often be these big hooks for these big catches that you can hang off. And so you usually have this metal bar leaning up against some kind of wall or support structure, and then the catch comes in, and so you can kind of lean it out. There'll be a cable here and a cable here. And of course the cable is keeping the whole thing from rotating and falling on the ground. And then you have to hang your catch. But of course, if you put too big of a catch on here, then this cable up here could break, right? Or the forces down here could be so large that they compress or break or bend this support beam. So, there'll be a sign off to the side that says maximum weight is, and don't put more than that on there. If you put more than that, you're going to break something. There's going to be damage. So in this case, the problem says that we have a 10,000 Newton shark supported by a cable that is attached to a 4-meter rod. So this hanging rod is up against the wall. It's 4 meters tall. It can pivot around its base. Calculate the tension in the tie rope, and so there's this rope over here between the wall and the rod, and assuming that the rope is holding the system in the position as shown, so they give us 60 degrees here, find the horizontal and vertical forces exerted on the base of the rod and go ahead and ignore the weight of the rod. So they asked for 3 things, right? Earlier, calculate the tension in the tie rope and then the horizontal forces. So not a surprise they asked for 3 things, because how many equations am I going to get out of here? 3 equations to solve for 3 unknowns, right? Some of the forces in the x, some of the forces in the y, and some of the torques. And again, some around the torques around any and every axis. So pick any axis you want. All right, well, like all these problems, let's come back here and get a good physical understanding of what's going on, as well as step 2, which is that free body diagram. That will help us finish the problem by giving us something to focus on as we do step 3 and write out the equations, and then step 4, solve those equations. So I'll clear off the board here and say, okay, if I came over here and was looking at the free body diagram, as well as trying to understand the problem here, I would be saying, what forces are on it? Well, there is clearly the force from the shark itself that is pulling down on it. And as that is pulling down on it, that would tend to make it pivot around this base. So that is why there is a rope here. Did they put 20 degrees there? 20, what is that, 20 degrees? And so there is this rope that has a certain tension in it. And of course, as we said earlier, too much weight here would put too much tension and the rope would break. So there's going to be an upper limit. But assuming we haven't exceeded that upper limit, this would have a certain tension based upon the weight of this shark here. They do say that this angle is 60 degrees. So that's going to help me in my dealing with the problem. They also said I could ignore the weight of the 4-meter support rod here. So I do know its length is 4 meters. So that'll be an important piece, but I don't need to worry about the force of gravity. And so the only other thing touching the rod is this place down here, which again, notice, it is a rigid object. And with a rigid object, I'm never quite sure what direction the forces are, and so I'll write it in terms of its x and y component. But the rope on the top up here, there was no question in my mind about what direction that was. It's the same as the direction of the rope itself. So again, notice I'm not saying the force is at 60 degrees. But up here, I am saying the force is at 20 degrees. So the rigid object I've got to write into its components. The flexible object is the easy one. I know its direction. Okay? So I think I've got those first 2 steps down, a physical understanding of what is going on in this problem and the free body diagram of what forces are on there. So let's write out the equations. So I would say here, let's write out the forces in the x direction. So in the x direction, I can see that this one would be moving over here. So I'll write this as F x, force in the x direction. Both of these are in the y direction. I'll ignore that. Now this one has a component, if you will. It's what you might call the second quadrant sticking out here. But if I wanted to know the horizontal piece, then I would have the cosine of the 20 degrees. Or is it 60 degrees? Yeah, it's 20. I didn't want to go that fast. I wanted you to think about it. But yes, it is the 20. And it's in the negative direction. How about the forces in the y direction? Well, I guess I have the Fy from the base pushing up. I got the shark at 10,000 pushing down. And then that tie rod is actually lifting slightly up, isn't it? And so it would be T times sine. Sine of 20 degrees. And it would be a positive direction. And those, I suspect, are probably going to be the easier ones for you because they have to do with forces and components of forces. And we've been doing that since chapter 5. But new to this section here is the torque, although we now have been doing it for a few weeks. But let's calculate the torques. Now remember, the torques come out to be 0 around any axis. So I would suggest you pick one that is going to make your life the easiest. And as we saw in the other two, and we'll see here, if we pick this point right here, then how much torque do you get from this component and that component? Yeah, 0. And so you're going to get torques from just those two. Let's start with the shark. And since this is new, help me fill this one in. What would be the distance away? What's R? 4 meters. Okay, good. How much force am I getting from the shark? Maybe I'll put right above it, RF sine theta. So it's 10,000 newtons. Okay, good. What angle? Is it 20? 60? 30? 90? So what do we mean in here? What is theta? The angle between what? Between R and F. All right. And so those of you who said 30, yes, that's it, right? This is the R out to here. And this is the F straight down. We're talking about this angle right there. That's 30 degrees if this is going to be 60 and we've got straight down. So we've got a 90 degrees here, we got 60 degrees there, we got 30 degrees there. So this torque would be something like that. Now I guess I should ask positive or negative? Negative. Yeah, negative. That shark's going to be pulling it and rotating it in a clockwise direction. So there's my torque. And of course I have the torque from this tension up here, this wire here. All right. Maybe I'll start off with the direction. What direction is the torque? Positive. What is the distance? What's the R? Oh yeah, that's 4 meters. That's not a hard one. What's the force? T. What's the angle? Is it 20? 60? 30? 90? 80. I'd go with 80. Where did the 80 come from? Well, that would be another 60 because these are alternate interior angles, right? And it's the angle between R and F, so it's that whole angle there. So it's a sine of 80 degrees. And so I thought this one made a really good one. It really kind of hopefully hammered the idea of what do we mean by the angles. Because here is the angles to get the components. That was a little different than the angles to get the torques. And that's really what I want to make sure I pointed out and repeated here. Because to get the components, we're looking at the angle from the grid, if you will. From the x-axis and the y-axis. But when you're calculating torques, you don't care what the angle is in relationship to the grid. You care about what the angle is between the R and the F. Totally different set of definition of the angle. And so when you write out a picture like this, and you have angles like 20 and 60 in the picture, but yet your equation has angles like 30 and 80, it hopefully very much illustrates the difference between those angles that are in relationship to the grid and the angles that are connected to the torque. Of course, you can see again this bottom one right here is probably the perfect one to calculate first as we go to step 4, because it has only one unknown in it. And that unknown then could be used back in these other two to get the other two unknowns. So solving for this one first, this would be 4 times 10,000 times the sine of 30, which I guess is a half. I'll just hit enter on that. It's a negative number, but when I bring it to the other side, it's positive. So then I can divide it by 4 and take that result and divide it by the sine of 80 degrees. And I get a tension of 5,077 newtons. And so there's the tension. Did you get a different number? Okay, well, I want to make sure I didn't, yeah. All right. I know I can often hit buttons wrong here on here, but anyways, so I got 5,077. Assuming you guys got the same number, I'll move on here, because now that means I could get, say, the force in the y direction here. Because if I move this to the other side, that's 1,000. And I then can subtract the 5,077 multiplied by the sine of 20 degrees, and I come up with the force in the y direction of 8,260, and I'll round it up, 4 newtons for the force in the y direction. And then back over here for the force in the x direction, that would be that tension, the 5,077, and then multiply by cosine of 20, and I get then 4,771 newtons for the x direction. And so there's, like I said, another good example. And now that I think we hopefully have taken, some good time to go through these, maybe I'll go a little bit faster now here. Let's keep going with these. Let's look at 45. 45, I think, has some nice pieces that let you think about torque. Particularly this one here. It says in 45 here that a force is exerted on a uniform rectangular cabinet that weighs 400 newtons as shown in the figure. So here's this cabinet. They give its dimensions. It looks like it's a meter tall and 0.6 meters wide, and about midway there's some kind of force on it. So the cabinet's about this high. And it's probably, well, here, this is 1 meter, so it's this high, a little bit higher than this table. And 60 centimeters makes it right about there. So the cabinet's about this wide, it's about this tall. They don't say how deep it is, but they are saying here that somebody's going to grab it. It looks like they're grabbing it about the middle, and they're going to pull it. It looks like they're pulling it upward at an angle of 37, okay? And so again, just trying to get a picture of what's going on here. They do say this at the first sentence here, right? The force is exerted on a rectangular, so we know its shape, and it's uniform. So that means it has the same weight all the way through. Probably not realistic for a filing cabinet, since it is either A, empty, or B, full, and the stuff that is full is probably heavier than what the sheet metal was made out of. But nonetheless, I think they're just saying, where's the center of mass in all this?
The center.
Yeah, the center of the object. The center both vertically and the center horizontally. So we need to know the center of mass. Because again, part of this is what's the torque? And part of torque is where is the position of that force. And so that's why with the other problems we had to keep asking where's the center of mass, and this one too. So they're giving us information that will tell us where the center of mass is. A, the cabinet slides with a constant speed when a force of 200 newtons at a height of 0.4. Oh, I guess it's not quite halfway. 0.4. Find the coefficient of kinetic friction and the position of the resulting normal force. Okay? So this is a little different than any of the other problems we've done. The other problems, they were all at rest. Fair enough? This one is not at rest. This one's actually moving. So I thought this would be a good extension of our logic that we had done. Although, as you'll see, it really doesn't change much. It's also got another nice piece because instead of giving us all of the forces, they say find the position of the normal force. Well, let me draw the free body diagram here. Step one is, of course, understanding the problem. Well, I think we did that. Step two, then, is what is the free body diagram? Well, as we just said, there would be a downward force in the center of this object coming from gravity. And as they pointed out here, there is some force right here, which they said is at a height of 0.4 meters, is pulling it at an angle of 37 degrees and with a magnitude of 200 newtons. So that's that force that is causing it to slide. All right, so we got gravity and everything touching it. And obviously one thing's touching it is whoever is grabbing this to pull it sideways. But what other forces are here? Yeah, very clearly there's friction. You're sliding it across, so the friction would be this way. And so F of K, kinetic friction. And what other force?
Pulling force.
I guess I already have the pulling force right there. There's the 200 newtons. The normal force, right? And so underneath this cabinet, the ground is pushing up. Where is the ground pushing up? Well, you're probably more realistic. It probably is uniform. It's probably spread out, but maybe not uniformly. There's some average. So just like the mass is all spread out, there's some center of mass. Let's call this the center of the normal force, okay? But there's some equivalent position. But why would I say it's not necessarily at the center? Right, we got to make sure the torque's balanced. So as this thing slides along, we need to make sure it doesn't rotate. It's only sliding. So what do we know about the sum of all the torques? It's still zero. Even though the object is now moving, it's still not rotating. And so the normal force, let me just put, say, here, and say that the normal force is some distance x from that corner. And what's going to happen is that normal force needs to be at such a location so that the two things match up. That is, the normal force has to create enough torque so it doesn't rotate. Let's talk about that one first. How about we just talk about this corner? Now remember, it's not going to rotate around any point, but I'm going to pick this corner. Because when I pick this corner, it looks like, to me, gravity is making it rotate in a counterclockwise direction. The force from this person pulling it is a counterclockwise direction. The normal force is also at a clockwise direction. But if this force is pretty strong, then we would want that normal force to be in here tight so that you don't get too much torque making it rotate. Fair enough? And so we can control how much torque, or I should say nature can control how much torque by the positioning of the torque. But we don't want to change the magnitude of the torque, because what else has to happen here? Exactly, the vertical direction. The vertical direction, you have gravity pulling down, and then a component pushing up from here, but then the normal force pushing up also. So the normal force has to be a certain amount, a little bit less than the weight of the object. And so we don't want to change the numerical value of the normal force. So we have to have the correct numerical value of the normal force so that the object does not go up or down. But we also have to have the correct amount of torque so it doesn't rotate, and that's why the different position can be there. And that is what I mean by step one. Understand the problem. What physically is happening here? And so I think I've got now both step 1 and 2 done. The physical picture of what is happening in the problem, as well as the free body diagram. And of course, once I have that, now let's go to step 3 and write out these equations. And so adding up the forces in the x direction, I guess I would say the normal force, only y. Gravity, only y. Doesn't this have an x component? So this would be 200 times the cosine of 37 degrees. And then minus the force of friction. Fair enough? And those are the two forces in the x direction. And those have to add up to be what? Now, before you answer, remember we said they have to add up to 0 when it wasn't moving. This one's moving. So now what does it have to add up to? Still has to add up to be 0. Because the sum of all the forces equal what? Mass times acceleration. What's the acceleration in this problem? 0. So this really isn't a different problem than we've been doing, other than I might call it a dynamic equilibrium instead of a static equilibrium, because thing is actually moving to the right, but it's not accelerating. It says it is being pulled to the right, it's moving at a constant speed, so the acceleration is still 0. So that's the same mathematical equation whether it was stationary or moving with a constant speed. Let's add up the forces in the y direction. Again, coming to the free body diagram, I can see that the normal force and a component of my hand are lifting up. So I would have normal pushing up, and I would have 200 times the sine of 37 degrees also pushing up. So those two are pushing up. The one that is pushing down is mg, and that has to equal 0. And of course, the one that I think gives us the most troubles because it's new to us, but the one that is probably the most interesting here is the torque. And so I would want the torque to be 0 around any axis. So you can pick any one you want. Keeping in mind, though, pick the best one, the one that's going to make it, the easiest for you. And I'm thinking already, obviously when I set it up, I was thinking that point. I suppose an argument could be made that maybe that's not the best one. But what I like about that point is how much torque do you get from the friction? Yeah, it's going to be 0. Remember, this is the calculation for the torque. And this sine of this angle is going to be 0 degrees. No matter where you say the force is acting. You could say the force is maybe in the middle. Okay, fair enough. But it is acting this way, and you're going to draw an arrow that way. And so regardless of what the value of r is, and regardless of the value of f, you end up coming out to be 0. And so that one goes away, and that means the only unknown that shows up is the normal force and the x. But that's what we would like to show up in our problem. That is what the problem is leading towards. Where did it say? The cabinet slides at a constant speed. Find the coefficient of kinetic friction and the position of the normal force. So let me calculate the torque about this point right there. And so I guess I will start with normal force. The distance away is x. The value is n for normal force. And the angle between those two is 90 degrees. And it is pushing it in a clockwise direction. So I'd say that's a negative torque. Again, imagine putting your finger right here and pushing up. Makes it rotate in a clockwise direction. So notice it's not the direction of the force. The force is up, but the torque is negative, right? The torque is the direction of rotation, not the direction of translation. So this is a negative torque. Gravity, well, its distance is half the width of the cabinet. So they said the cabinet was 60 centimeters, so half of that, because it's uniform, would be the 0.3 meters. The distance away, well, this is worth discussing again. Drawing a picture. It's the same one we had with that crane. But there is r, there is theta. Isn't this distance right there the r sine theta? The perpendicular distance. And so when I came over here and put in the r and the sine theta, that's where the 0.3 came from. It's both the r and the sine theta together. And of course the amount of force is mg, and I think they gave me mg, didn't they, with the force. The cabinet weighs 400 newtons. So this is 400 newtons. And of course, is it a positive or a negative torque? Yeah, I'm going to say it's going to go in a counterclockwise direction, so it is positive. The opposite of that one. Good. And then, of course, this last force does also apply a torque. There's your distance away. There's your r, 0.4. The magnitude of that force is the 200. What's the angle?
127.
Yeah, you see the 127, right? It's this whole angle between the r and the f. So it's the 90 plus the 37. So 127. Would it be a positive torque or a negative torque? And again, visually, I think you can see, if you're kind of pulling this, that would make it go in a negative direction. You might even want to do the right-hand rule on this one, just to confirm. You put your fingers in the direction of the first vector, so there's the r, and adjust it so you can close towards F. There you go. And now my thumb is in. So, yep, it's a negative torque. All right. I guess earlier on back here, I probably should have put 400 newtons for the weight of the object, because looking now and going to step 4, solve the equation, I can see that there are two unknowns here, but only one here. So I'm going to jump to that one, and that will tell me what my normal force is. And so my normal force would be 400 positive when I move it to that side, minus a 200 times a sine of 37. coming up to a normal force of about 280 newtons. So there's my normal force. Now that'll help me a lot up here, because this one has only the one unknown, the force of friction, and that would be 200 times the cosine of 37. And so that's 158 newtons. And that has to equal the coefficient of friction times the normal. So the coefficient of friction would be this. Oh, sorry, I rounded the wrong way. Where did I go? Pardon me? There, that should be 160. Right? Yeah. Yeah, 160. Then if I take 160 and I divide that by the normal force that I just got in the last step, 280, I get a coefficient of friction of 0.57. And so that, of course, bring me back to chapter 5, but I know you're really good with chapter 5. We've been doing it a long time. You've been reviewing, getting ready for the final, I'm sure. Yeah, question?
Where's the 0.4 coming from on the height?
Oh, height, right here it's given 0.4 in the problem. It says h is 0.4.
Oh, it's H
Oh, okay. Yeah. So how high is that? 0.4. Now that being said, now we can get to the harder one. So this time I think the torque is the harder one, but now that we've solved this one for n, we can go through a few algebraic steps here and get the value of x, which was this question, what is the coefficient of friction? I got that. And then what is the position of it? And so maybe I'll just, I'll do this one here first, I guess. 0.3 times 400 minus 0.4 times 200 times sine 127 degrees. So putting all of those together gives me 56.1 Newton meters. Moving that to the other side. Then I can divide that by, well, that's 1. And then divide it by n, which we said earlier was 280, and that should give me x. So x is coming out to be about 0.20 meters, or about 20 centimeters, which means in my picture, 20 centimeters is just a little bit to the right of center, maybe right about there. So that's the true location of the normal force. It is not at the center of the object. It has moved over a little bit. That's a nice way of saying we need enough force to support the weight, but very little torque to keep it from tilting. And that's how it's set up. And I think it'll help us within the next question once we understand the physical concept here, because then B says, taking F to be 300 newtons, find the value for H for which the cabinet begins to tip. All right, so they're going to change things up on us a little bit. They're going to say, all right, increase this force to 300. Now, let the height be a variable. But let's just say, before we move the height, let's just say we increased this amount of force to 300. What would that tell me conceptually? Well, I guess in the vertical direction, I would start off by saying that would mean I need less normal force. Fair enough? Also, because this force is increasing, which is part of the negative rotation, I would need less torque from the normal force. Now, I'm already getting less torque because the value of the normal force would go down. But its position could also go over a little bit, right? And in fact, the second part of B is to say, well, what happens as H gets bigger and bigger and bigger and bigger and bigger? And of course, as H gets bigger and bigger and bigger, N doesn't change. You still need the same normal force to lift the weight of the cabinet. But as H gets bigger, the torque you're getting from here gets bigger and bigger and bigger. So what happens to the torque from the normal force? It's got to get smaller and smaller and smaller to keep it balanced. So the normal force is going to move over and over and over and over. And at some point, the normal force can only move over to this point. And then you're not getting any torque from the normal force. You might say that your torque then is balanced from gravity and this person pulling on it. And if you go any higher than that, then what's going to happen to the cabinet? It's got to tip it. It has no option not to tip anymore. You're giving it so much torque from the person pulling it that it doesn't have enough torque from gravity alone to fall back. Which is why then when you usually grab a cabinet near the top of it and pull it, it tips. When you grab it near the bottom and pull it, it slides because of the whole torque issue. And that's what they want you to see here. So again, a good physical understanding. Well, I tried to switch to a different color, but the orange is maybe a little too close to the red for you to really see that. So maybe I will go blue and blue. But let's write these equations out. What would change over here? Okay. Yeah, maybe I should just, well, I'm going to start again, but maybe I'll just do that. I mean, that would be the first thing that changes, right? I mean, and clearly I have some kind of new force here. So this is changed to a 300, and that has changed to a 300. I'll go to the bottom one in just a second, but clearly that would change these numbers then. And so now the normal force would be this 400 minus the 300 times the sine of 37. And so we're talking about a smaller normal force of 219, which is what I said earlier. You're going to get a little smaller normal force. Okay. Oh, which of course, once you get yeah, well, if we're going to do it at a constant speed, I guess this one changes. I'm not sure we even need to talk about this one, since they didn't say redo the coefficient of friction. But since I brought it up, I will. 300 times the cosine of 37. And so the force of friction now becomes about a 240. But the one that really changes over here is this one here, because we said here that the H, which was 0.4, let me now put as an H. That's where it is. And we are now pulling with, instead of 200, 300. And so that's this negative torque coming from this one. Now, gravity, nothing's going to change there. We're still going to have it at its same position, and we're still going to have a value there. This one, though, they're saying, what would it require to tip? And that was a key there. What are they really telling me about x then? X is 0, right? And so as long as x doesn't equal 0, that means there is a torque here that is balancing it from tipping this direction, a counterclockwise rotation. But as this gets higher and higher and higher, eventually that one beats that one. And that's this piece right here. Which actually, now that I think about it, I don't even need that. That falls out of the equation. I thought I needed it, but I guess I really don't. I just need to solve this then equation. And so you're saying that the 0.3 times the 400, subtracting off the h times the 300 times the sine of 127 degrees, you want that torque, I'll say equal to 0, because when it's equal to 0 is when it just begins to tip. And then, of course, if h is greater than that, then the torque is greater than 0, and it really does tip. But now I can solve this for h. And so h must be less than or equal to, otherwise it would tip. And so I guess I'll move it to, oops. Did I want to? I guess I want it the other way around. When it begins to tip, when h is, well, I'll do 0. When h is too big, it begins to tip. And I don't want it to tip. I want it to go the other way. So I want this to be greater than or equal to 0. So, yeah. So now, moving this over to here, h must be, yeah. So when it's not tipping, h is less than. And so when it's not tipping, I want this negative torque to be small. Okay, but coming to my numbers then this is a 0.3 times a 400 here. And then I can divide that by the 300 and divide that by the sine of 127. And we're looking at about 0.5 meters. So if I go more than 0.5 meters, it just begins to tip. Yeah.
What happened to the normal force times distance?
That went to 0 because x is equal to 0. Yeah, yeah. And so that whole term went to 0. Yeah.
If we pull from a lower point, would the torque still be negative or positive?
If
The height is lower, like
the torque is always going to be negative, no matter where I grab it on here, because imagine again pivoting here. If you pull it, that's always going to make it go in a clockwise direction.
even if you pull like this, wouldn't it go back though?
Not if you're pulling this way. To make it tip that way, I have to push it in that direction, right? Yeah. But anything that is in this direction, here, 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 or here, is always going to be making it tip in that direction. All right? Well, let me finish up with a hint on number 51. Like I gave you with those two discs, and some other hints that students have struggled with in the past. 50, did I say 51, 57? Which did I write down here? 51. Students have struggled with this in the past. It's a really good problem. And it seems simple enough until you sit down and start working on it. And I'll give you some little individual hints, but the big hint is be careful with how you set up your free body diagram. Because if we read the problem here, which has to do with this step ladder and this painter who looks like 3 meters up a step ladder, that the total height of the step ladder is 4 meters. So the person is 3/4 of the way up. It's a very big ladder, so it's spread out. The contact points of the ladder are A and B apart here. But it says here a step ladder with negligible weight, so we don't need to worry about the weight of the step ladder itself, is constructed as shown. Now the painter, who has a mass of 70 kilograms, stands on the ladder 3 meters up from the bottom. Now assuming the floor is frictionless, so in other words, they are giving you something away right there. They are saying in your free body diagram, if you draw your ladder here, these contact points, which they label as A and B, would have forces that you might want to call force A and force B. But without any friction left or right, we know that those are only the normal part of it. And so you can imagine putting this on a floor that is, maybe a pretty slick floor. Maybe this painter is in a large lobby of a building and this is a marble floor. And so it's really slick. There's no friction here. And so obviously you don't want to fall. And so and even if there was some friction, you wouldn't want to rely on the friction to keep you up. You want to say if there's no friction, it will still support me. And so there is what that first part is trying to say here. Assume the floor is frictionless. And then it says, find the tension in this crossbar. And it goes on to the next page, connecting the two halves of the ladder together. B, find the normal force at A and B. And then C, the components of the reactionary force at the hinge at the top of the ladder, point C. Okay? Suggestion, treat the ladder as a single object, but also each half separately. And that's what I want to give you. Really the same hint that the author gives you is watch the setup of this. If you were to put the whole ladder for the free body diagram, then what forces do you use? External forces only. So the only external forces here is the weight of the person pushing on the ladder, and then the normal forces coming from the floor. You would not include the force up at the hinge where the two meet. And yet that is one of the things you're being asked for. So my point being here is this is a great free body diagram, but it's not going to get you where you want to go. To get the answer that they are after, you want to look at maybe half of the ladder. Force at A. Weight of person. Because then the other force is the tension in the tie rod between the two, and the forces at the hinge. And so I'll say it again, the neat thing about internal forces is Newton's third law. There's always an equal and opposite. So when you go to add up the sum of the forces, we only ever add up external stuff. So when a question like this pops up and they want to know something about, say, the hinge between the two, you can't include the whole ladder because you've got to make it an external force for it to show up in your equations. And so that's an important step. And so that's why the author is saying, make sure, and I'm trying to give you a hint, you do half the ladder. And that would have been your clue. If I wasn't giving you the hint or the author wasn't giving you the hint, that would have been your clue to do half the ladder because you've got to make it an external force. Now, with that said, notice also that if you set this up first and by itself, there's too many unknowns. So you're going to have to also use this free body diagram. See, this free body diagram is really nice. It will actually give you the information of what is the force at A and what is the force at B. So then when you do this free body diagram, you can actually then know the force at A and you know the weight of the person, and now you have your three unknowns. Three unknowns with three equations. This by itself would have been four unknowns with only three equations, and that's going to run you into troubles. So you have to do both free body diagrams.
Would the sum of the forces in that one have to equal 0?
Yes.
Okay.
Or let me ask you, is that half of the ladder moving?
No.
So what are the sum of the forces? 0. And what are the sum of the torques? 0. Right. And that's the whole point of this chapter and of this lecture. So I'm hoping that it was helpful. Obviously, your test is coming. I'll say it again, although maybe it doesn't matter because you just have to work from wherever you are today. In 5 days, you have a test on the tough material for the semester, and we haven't given you anything new for 7 days, and we won't again until we come back from the test. But obviously, get it to sink in. And if you